We'll get started. I wanted to make sure that I stayed true to I followed that I didn't break the two cardinal sins in presenting. One, I'll never read a slide to you. Second, don't ever end up late. So I want to make sure I get you out of here at least early or on time at the latest. So I'm sure you've spent a full day with us. You've got emails and Blackberries and crises to handle before we entertain at Mr. Jevitt's house, so we'll get started with my presentation. From the agenda standpoint, this is a conclusion. We'll go through this presentation of choosing the right material for the job, open it up for question and answers, not only for my presentation, but for anything that you saw today, Dr. Mooney's presentation, any of the technologies, or anything that we haven't shown you. Don't hesitate to ask now, or if you'd like to take one of us off to the side today, sometime down the week, you think, oh, I wish I would have asked that, feel free. That's what we're here for. A little bit about myself. I am the Director of Business Development and R&D here at Romart PMC. I actually started my career as a former model. What? I was actually paid $2, $1 for each photo shoot, to take photos at what was then DNS Plastics, which eventually became Solvay, which I grew up in the farm club. But I realized that $2 wasn't enough to retire on or eat. So I basically worked various engineering, sales, and marketing roles, all in the compounding realm, mostly with TPO. As I mentioned, first with DNS Plastics, what was then moved on to Solvay. Solvay was bought in 2009 by LyondellBasell, and then I spent a few years at Mitex Polymers. From roughly about 2001-ish, met Mr. Beers. We started to work on specifically formulating TPOs for extrusion thermoforming. Up to that point, it had been almost all injection molding, and being very successful, mind you, to the point where it's now roughly a 600 to 700 million pound industries, and on almost every vehicle that's in the parking lot, interior and exterior. Automotive was very glamorous, as the downturn Dr. Mooney explained, and I decided that sheet thermoforming was far too compelling not to continue to pursue. So I joined PMC around July of 2011, and I'm responsible for product development, R&D like the title, and also from the commercial standpoint with our decorative films. One of the things I do like to point out, though, however, I am not an actual professor. I do not have a doctorate, and I'm nowhere close to rocket science, even though I've taken a lot of engineering courses twice. So you'll hear these guys call me professor and all this, and it's a little disturbing and bothers me a bit. But I will say, though, the one thing I am absolutely not is an expert, and I'll correct folks when they say that, because I feel that our field and any of the scientific fields are always growing. We're always challenging. That's what makes engineering and science and research fun, is things that you thought were hard and fast and chiseled in stone can sometimes be challenged. I tell the story of one of the people I looked up to growing up is my grandfather, and he was not a formally educated man, worked up through General Motors, and became an engineer, a true engineer, where you made stuff, you fixed stuff, you solved problems. And I remember it was a Thanksgiving in the early 1990s when he asked me, he said, "What do you guys do over there at DNS Plastics?" I said, "We make TPO." I was pretty proud, because it was a growth product in an emerging market in automotive. He said, "That stuff's garbage." When I was designing the Oldsmobile 88 interior, blah, 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 I stopped hearing at that point. He said this stuff warped, it sagged, we couldn't work with it. And I thought, wow, this is something I'm making a living, eventually a career on, and a guy I looked up to who had biases toward liking anything I did had a bad experience. And so what I look at is expertise and biases. We all have them. That's what makes what we do well in our jobs. That's the benefit of experience, are these biases. But just acknowledge that they're there. And one thing I like to do when we're working on any project, we talk about selecting materials and what you think you believe. A little snippet from Lisa Kudrow's character Phoebe in Friends reminds me of how that can be a little dangerous.
Uh-oh, it's Scary Scientist Man.
Okay, Phoebe, this is it. In this briefcase, I carry actual scientific facts. A briefcase of facts, if you will. Some of these fossils are over 200 million years old.
Okay, look, before you even start, I'm not denying evolution, okay? I'm just saying that it's one of the possibilities.
It's the only possibility, Phoebe.
Okay. Ross, could you just open your mind like this much? Okay? Now, wasn't there a time when the brightest minds in the world believed that the Earth was flat? And up until, like, what, 50 years ago, you all thought the atom was the smallest thing until you split it open and this, like, whole mess of crap came out. Now, are you telling me that you are so unbelievably arrogant that you can't admit that there's a teeny tiny possibility that you could be wrong about this?
There might be a teeny tiny possibility.
Can't believe you caved.
What?
We all know evolution's real. Anyway, it wasn't a social commentary. I just felt, I saw that one time and said that sums up when we talk about materials and you talk about the instance from my grandfather in Thanksgiving versus things that we learn every day out in the thermoformer and the extruder, and we add new things that we're constantly challenging what we think we know and replacing with things that we can prove and demonstrate time and time again. So I thought you'd enjoy that versus me plagiarizing it, making my own, and I thought I'd just show you through YouTube. Yes, of course. So Roger said, you know, what should we present? What would some people like to see? And certainly not the reheated materials 101 that I've given about 1,000 times, and I think most of you have seen. We wanted something that is useful and informative, and especially in today's day and age, we skim things. We don't really have full attention to anything. The BlackBerry, the iPhones, emails, the phones ringing, customers, suppliers. So we want things that are distilled down, that are quick, almost triage type things, tidbits that, granted, this isn't going to be able to turn you into an expert, which I hate the word, but in terms of being able to decipher this, that's what the team here at PMC is to help you do. This is just at least start the thought process or build some framework so that you can start to have these types of discussions with your designers and your customers. So Roger said, let's choose the right material for the job. I thought, okay, well, why would that be important? I thought of 3 key reasons. The main one is the pain of getting it wrong. If you dive into this head first without giving it thought, and you'll find I really don't talk about materials until after the first break we have. It's the methodology. But if we choose the wrong thing, it can jeopardize the success of, and timing of a particular program. You've got customers who expect you to deliver and deliver on time to what you've committed. So if you don't, you have unmet expectations, of course. And ultimately, as you represent this part, it has our name on it as sheet, it has the resin supplier's name on it as the resin, and any other complementary goods. A loss for that is a loss for the whole team. And then lastly, Peter pointed out, these designers at these OEMs are going to say, look, I had a bad experience like in the Oldsmobile 88 headliner, and I'm not going to use thermoforming again. And so getting the pain of getting it wrong is too strong to not make this an important topic. As Peter pointed out so in depth, and Chris touched upon, the world has changed. I'm here at PMC because the world changed in 2009. You look at the 3 basic areas of the supply chain, and the resin suppliers are squeezed. There's no money and margin left. And what that means is you've got less support. In our glory days, back in the Solvay era, we had a development center in Auburn Hills, Michigan with a paint line, injection molding machine, and CAD software, and field tech service guys, and it's all gone. It's all gone. And really, that was just a byproduct of the model that GE built a generation before that. Not only would they develop resin, they'd market it, they'd help you process it. Hell, they'd even help you fund equipment and tooling to help launch that particular product. All that's gone now, too. The sheet extruders, because of all that service support, it created a culture where these guys were just viewed by their customers as converters and thereby became really pass-through guys. There wasn't really hard and fast development groups, technical support. You just had to make sure that you didn't screw it up for the resin team that set up the approvals and the materials for you. And that, of course, now is having to change. And then lastly, with productivity, which we've all felt, so the macroeconomic data we've all felt with do more with less. Wear a lot of hats. So these OEMs are no different. Also, all these design teams that would sweat all these details, do all this testing, really be a collaborative partner. Nope. Bring me a turnkey solution or don't come in, because I don't have time. And if I don't see a solution, I'll just go with what we did the time before that. So you get this perpetual rubber stamp effect from the OEM community. So if they liked injection molding the last time, the chances are they're going to be injection molding again the next time. So we've got to be able to break that. The other is sustainability. Now, it's preaching to the choir a little bit. Obviously, firms like yours, you're out looking, you're polling and queuing up the supply base, you're taking active participations, whether it's things like this, trade associations, but really it's innovation, the thermoformers that will survive. And when I use sustainability, I use the $sign one, not this green stuff that really, it sounds good, but until there's some hard economic meat behind it, I'm talking about the true sustainability. It means pay your bills, pay your employees, be community reinvestors. You're going to find that those processors who become more actively involved in this, what I'm going to outline, are going to survive. We saw it through the downturn. I've been through a lot of thermoformers, and the ones that I see that are strong, you can tell are profitable, have mastered their process. They've added value add, complementary things. So it's not just shoot and ship, as we used to call it in injection molding. It's assembly, systems, bolt-on stuff. We have a big customer in Minnesota that some of the big names, Arctic Cat, John Deere, and others, these guys do full cab systems, design to functionality to decorating. So they bring that on and offer it as a service, as Peter outlined. Bring me solutions. I don't have the time to be able to piece them together. And what that yields is, if you have a good track record, chances are somebody's going to pick up the phone again. Hey, this is Mark over at XYZ OEM. I'm in a pinch. I got to launch this thing in 3 months. I need your help. And really, that's ultimately what's going to grow the pie as we compete against other processes like rotomolding and injection molding. So the goal in selecting the right materials is always been, and we're human beings. We like variety, but we don't like too many choices. So boil it down to options. Give me a good, better, best. When you do that, you often help wash what you're being told is wanted, and based on their choices, really see what is wanted. It also helps you align expectations. So if you say, here's the good option, but here's some of the trade-offs, here's the best, and here's the trade-offs for that, now you've addressed it multiple times in different formats, so the customer at the end doesn't say, well, that's not what I thought I was going to get. And ultimately, with options, chances are your chance of success is 3 times as great because you're not promoting one system, you're giving them options to choose. And we like to buy this way. So it falls into most buying options. So how do you do that? The best way to provide options is to diagnose, which is a medical term, but also if you look in Webster's under the third outline, it's really to scientifically determine the needs through examination. You never have 100% of the information. It's impossible because most of the time the teams that you're working with, whether the processors or OEMs, don't know. But the ability to diagnose these help you increase the chance of success as we outline. So I'm going to give you 10 areas to consider even before talking about materials. Because if you look at these next 10, then you'll have a greater chance of at least narrowing down the field. Because the material options, even though, again, as Peter pointed out, catalyst technologies have decelerated. No new catalysts, no new polymers. No new polymers means the portfolio of products that we have, we've got to find different ways. We've got to be the Taco Bell, if you will, and make new products basically out of tortillas, beef, and mystery ingredients, and market it as new. We're not having Taco Bell tonight, but. So the 10 key topics to consider are, and in no particular order, but sort of, is timing is very important. Obviously, if you've got a crash program that's got to launch in 3 months, you don't have the time to go out and try to develop a brand new product. It just doesn't, it's not feasible. But when you look at that, that's simple, everybody gets it. But if it is a takeover job, is there existing tooling? Do I have to take on existing raw materials? Did somebody pull the business and the sheet and the adhesive and the components from XYZ, and now you've got to find a way to deal with it? Because that can have effects to our world in color harmony, in gloss harmony, regrind. I don't want to take somebody else's junk, especially if it's questionable. And if the relationship was souring, do you think that regrind was well taken care of? Are there issues that you have to deal with? If it's a takeover job and because there's failures in the field, you got good lot traceability that those failures you're not going to end up picking up the tab for. And how do you know whose part is who? I do believe as we start to see the influences of the competition of other processes. I've been to a bumper factory that injection molds TPO, and they're using robotic lasers to etch, timestamp, barcode on every part. Now we don't have that need yet, but it will get there, and that will give us greater traceability, which then helps us do greater problem solving and ultimately remove extraneous costs from the system. If you do find that you've got the timing, then that helps you then outline your R&D time that you have available. Part and function design. What is the function of the part? And again, these are intuitive things, and that's on purpose, to then delve in some of the other components that you might not think of. But really, we start with, are these parts aesthetic? Are they structural, or are they both? And once that's answered, then you've got a good feel for what material or group of materials, what systems do I need to look at? Do I look at a decorative outer panel and a structural inner? If I go twin sheet, I've got to use the same material, so I have to make sure I'm doing a little bit of both. Design is huge. I put up here that a good design can make up for a subpar material, but a subpar design cannot make up for excellent material. And I think as engineers, myself, mechanical engineer with plastic specialty back when, is that as designers we've gotten lazy. If you look at the materials that were available to the first generation of engineers, they had animal products, you had stone, you had wood, and some of the basic metals. When you look at concrete, every building we inhabit uses concrete, but it has a tensile strength between 200 and 800 psi. There's no tensile strength to concrete. Well, how do you make buildings? Well, you make sure it's in compressive strength, which has 100 times that strength of its tensile value. So through good design, we're able to use something that has a severe mechanical limitation. Now, if I was to come up with a raw material that only had a 200 psi tensile strength, somebody would say, that's garbage. Well, maybe with a good design, it's not. When we get into that, what do you mean specifically about moment of inertia, and then how can design make the difference? And I'll give you an actual case study from my experience where it helped and also it hurt. A poor man's mechanical engineering, the first course you take is statics. You build bridges. You calculate the forces it takes to build a bridge. And what you learn is the first thing is the cantilever beam. And that's your standard thing poking out from the side of a building. And you're trying to measure how much deflection, force, etc. And so what you're looking at is to build a design through materials or through this particular part to resist bending. Now, what you've got here is one of the ways to resist bending is through the moment of inertia. What's the geometry of the part? So this piece of paper doesn't resist bending very well. It's basically that flat sheet. But if I was to just take this, put a simple crease in it, open it back up, it now does not flex down at all. So through just a cross-sectional geometry change, same material properties, I've now been able to keep this piece of paper horizontal. It's basic statics with design. But we see this in a lot of plastic part design, both good and bad. So case study. Program A was a backhoe cover that we worked on. This is TPO high gloss, 25% filled. It had about a 300,000 PSI flex modulus with a heat deflection temperature of 230 F. So we had this backhoe cover here, and these would go on the side of the engine. So it saw a fair amount of heat. We took this thing up to 280. The second part was an RV camper roof, much higher filled, higher flex modulus material than the first one. That really only had, this particular part had to perform at room temp. What were the results? Well, just through that previous slide I show you, geometry apart, this guy, 50 degrees its HDT, had very minor warp, no sag. This guy at room temp sagged 4 inches in the center here, because this guy acted more like the flat sheet of paper, even though the material had a higher flex modulus, than this guy over here, because this was a vertical piece of paper, did not want to sag. So we had this versus this in almost identical materials. So just some simple thought into basic geometry and design can make or break what materials you choose. Another important one, obviously, is service temperature, as we saw in the previous example. Both determining whether it's interior and exterior is important, because then we start to bring in the topic of UV stability. But really, we're talking about temperatures, both where we see a part that'll see the maximum and minimum, or service temp, and there can be a difference. So a part that sees maybe 180 degrees F for 20, 30 minutes is a whole lot different than this thing has to operate at 160 degrees. Plastics is just like any material, it's susceptible to creep, which is it's deformation under load, time, and temperature. So if you've got a coat hanger out of polypropylene, and it's got a heavy coat, on a hot day, that thing's going to continue to sag, versus if it just saw a little bit of high temp and then cooled off, well, completely different performance. Making sure you understand it's not just temperatures. What's this part going to expect? Rocks off the road? Are we going to have to look at sun load, if this is a black part, any particular color fade? Obviously, chemicals play a large role, not only in the field, but there's also chemicals in work in process. The marine guys are infamous for this. They love to clean with the nastiest stuff that you wouldn't put your bare hands in. Toluene, xylene, MEK. They love cleaning with this stuff because it works. But some plastics can be quite detrimental. The topic of specification. I know this is a busy slide because it's a very important topic. Specifications can both help and hurt. The first few items are, of course, in the help category. You can use a specification means somebody, maybe when they had extra head count, sweat the details of saying, all right, I'll take this data sheet and real part information from the field, and I'll create a performance spec that'll help my customer differentiate the performance points they need to hit. It helps protect the customer, because if I give my expectations, then I'm explicitly telling you what I need. I use Case New Holland because they do a good job for this particular type of specification. As a processor, a material guy, extruder, a thermoformer, it helps level the playing field too. So some lesser material has to go through this process, make sure it's validated and vetted before encroaching upon some protected business. And our quality guys sure love stuff to measure. If they can't measure anything, then the chances of meeting your expectation day in, day out are severely limited, because then you may have a communication gap. What's the color tolerances? What's the surface aesthetics that we've got to establish? But as you'll get into some of the downside, is this can limit your options. I'll show you here in a second a specific case study to that point. But really, as I mentioned, it's written off of past successes. So if you go to a mass transit spec that was originally in fiberglass, and it reads like fiberglass in the specification, the chance of you meeting it with a thermoplastic, even a system where you're using an outer and inner, are severely diminished, especially if some of those properties aren't necessarily needed for the application. A lot of these as I outlined there in the second to last point, is they focus on the what, not the why. So I'll see specifications that'll have extraneous data points, let's say tensile strength. I need a 21 MPa. Well, what if it's 19? No, I need a 21. Well, why do you need a 21? I've never seen a TPO part fail in tension, never. You've seen cracks and rips and all these other things due to design, but never in a tensile fail, because you're not making chain link out of this stuff. So making sure that it's not exactly what you need versus the why you need it. I'll also tell you, as a former material guy and a current sheet guy, I want to make sure I get my product on the print, as they say. There's significant barriers to change, and it means I've arrived, especially if I'm the first one. I have very little work to do. I've reached the mountain, and now everybody has to play king of the hill against me. So there's that dynamic that we've got to acknowledge. So some do's and don'ts before I get to the case study. Some of the do's, I encourage it. So all said and done, the pros certainly outweigh the cons. Especially as engineers, we like to be able to measure things. So do encourage it. Most OEMs these days won't, even though if you have an opportunity, won't sole source with a particular technology or vendor. The reason why, remember, the world changed. So you could have been with that company that I worked for a number of years for a product that worked very well for a number of years, and it was killed. Well, what do you do then, especially if you waited, and most did, or you stockpiled and the inventory went away? So making sure that you build it on the properties and not the specific product is what's key. Somebody else has brought it before, well, if I don't put a particular material, then how do I know what's approved? And that's an excellent point. And automotive gives us a lot of bad habits, but one of the good things they do is an approved source list. So you can still have your specification with performance requirements, and then if you vetted or through PPAP or whatever type of qualification, have a separate list saying, these guys meet that spec. So the spec stays evergreen, and this list can change. Companies go out of business, they fall out of favor, they change the raw material, whatever. But that gives you that versatility to accomplish both without limiting your exposure. Acknowledge that unless you're making a truly unique product, like we've done with Stratagen, we're taking one product, another product, we're really making a third product out of it. If it's somebody else's material, make sure you drill down to the transparency. You'll find that's one of the things that we tout here is we'll tell you what the resins are, if we can, unless we're making something unique. So if you want to know what type of TPO, what kind of ABS, because you're trying to get to that transparency with your customer, this is what we're trying to build the specification around, not Eric's 102 grade. That's hard when you're trying to determine where did this come from. Because what you find in some cases, if there's private labeling, they'll sometimes just cut and paste data from where the source was onto their own data sheet, and that can be dangerous. Understand that all these tests, and I'll go through the 7 majors in a moment, make sure you pay full attention to not only the test method, but also the conditions. And during a material seminar, I carry around a little thing of silly putty. I talk about the importance of speed in things like tensile tests. So if you take silly putty and you pull it apart fast, it'll break immediately. If you pull it slowly, I can wrap it around this room. And what you can see in some of the plastic tests is they behave the same way. Is you can get different values depending on the speed or the other conditions of the test and not know it. Now, is that being dishonest or disingenuous? No. It's just know that there's so many different test methods. There's ASTM, there's ISO, there's different conditions that certain companies have to certify. Remember, these companies don't have the resources anymore. You wanted an ASTM and they only offer an ISO, you're probably only going to get an ISO unless you want to test it yourself. So make sure you attend to the conditions. I highly advise not copying data from data sheets, as I outlined, and try to stay away from ambiguities. We had one customer I was working on, helping write a spec. He said, well, I think if I put UV stable, they'll get it. That's dangerous. What does that mean? How do I translate that? We had a particular color vendor that we had an issue with because we did the same thing. And it was an outdoor product, and it failed. And we said, well, we asked for UV stable. And they said, well, what is that, that to us is different than what we think you mean. And so you get one of these, you get unmet expectations. and everybody's name gets sullied, and you end up having a customer issue with it. So stay away from ambiguities. Be as specific as possible. Say, I need a color shift of X after so much exposure of xenon art. That's the way to do it. The other thing a lot of folks run across is trying to dictate compositional things. I had one customer saying, I want 6% carbon black. No, you want the benefit that that carbon black gets you in UV stability. So just put what you want as performance, because technologies change. They may come out with more effective additives. Maybe carbon black comes out of favor. Maybe some other material is discovered or technology. So you really don't want to dictate to the pizza guy how to make the pizza. You just want to tell him what I want on it, but I'm not going to tell you how to make it. So there's a big difference in that. It's important too, the more important and critical, especially from a safety perspective, is to utilize third-party testing and to do retains. And we do some of that here because you want to make sure that if you've got to do problem resolution, you've left breadcrumbs to be able to go back to and say, all right, is it our process? Is it the raw materials? Was it that lot? We've just run into an issue of that with one of the clear films. We had an issue with a lot. So we're able to go back to the original and prove that out to our vendor. No, it's not a gotcha event. It's just to help the chain do root cause analysis as fast as possible so you can deliver that option to the customer. And keep in mind, these are all things that injection molders live day to day, hour to hour, week to week, year to year. They're used to this. We're having to now compete with a level of sophistication and data collection. That's why we invested in the thermoformer, where you see the sag data, because it's trying to bring less magic and art and more science into it. So just some do's and don'ts from one guy's perspective. From a case study, here's this is off an actual print for an agricultural company that listed some requirements. And so I'm going to give you the good and bad and the ugly of it. The good is, this particular customer acknowledged that regrind is actually its own unique material. Meaning, if I look at regrind, especially when I'm dealing with multi-layer systems, I've now created a third unique material. So if you take A plus B and you grind it up and you put it back into A, it's different. So acknowledge those differences and say, look, we've thought this through and we're going to allow only 30%. So these guys have thought not just on the part, but how the part gets built along the supply chain. So I applaud that. The bad, though, is they got extruder exclusive materials. So meaning they just, by writing those two line items, said we can only buy from one extruder. This particular extruder has a captive compounding unit. So I guess if things are hunky-dory with that one customer and life is good forever and ever and ever, then that's all right. But in the real world, that can be a very limiting and certainly swing the leverage against you as a processor. The ugly is one of these grades is no longer offered. And this is still an evergreen print for parts that are made today. So again, that's where I think specifications are good. They're important. Base them on properties. And if you need to have specifics so you're protected, so you don't have your sheet extruder going off the reservation and giving you something you don't want, have a separate approved source list. And you'll be protected and still get what you want. Regulatory items. There's a lot, and there's more coming. You'll see an alphabet soup of various regulation, whether it's hazardous material, where it's trades protection under the guise of safety, like REACH for the European Union, the National Sanitary Foundation, so things that come in contact with potable water and such. You get this whole bisphenol A scare that comes out of polycarbonate-based stuff. Keep in mind, they put hundreds of millions of parts to these mice, and it acted like estrogen, this BPA. But it's determined that's not good for kids. Now, what they tell my daughters at school is everything that has a recycling symbol of 7 is bad. Well, I don't need that. That's a gross exaggeration because what Dad makes is a 7, and not all 7s are BPA contained. So there's a lot of hysteria and hype and arm waving, but it's out there. And you'll find companies like Nalgene, these bottles, hikers and stuff, not a one of them will not say BPA free on them. So the poor polycarbonate guys, first the CD-ROM and all that kicked them in the teeth, and now this BPA scare, and you're starting to find them having to reinvent and figure out how to take this out of there. Heavy metals, long looked at with a raised eyebrow because of some of the carcinogenic properties of the heavy metals. Some of the signage guys have actually had to go back and on a case-by-case basis use them because McDonald's still wants a red sign after the 4 trillion persons served, not pink. And guess what? Hexavalent chromium, pretty good material for red. But so you're starting to see globally that's a big no-no, and we don't use any here, FYI. So understanding that environment, and then you get into some of the performance stuff, namely flammability and toxicity. And I include this slide. One of the guys Roger and I served with on the SPE board, thermoforming board, him and his company, Kydex, wrote FR for Dummies, which should hopefully get published here in one of the thermoforming quarterlies. An excellent 101 to help navigate these waters. But basically, this chart sums up, not only do you have flammability, the burn rate, but you have how easy is it to escape from this particular mode of transportation, because we got to make sure that not only does it not burn, but what does burn is not toxic in terms of an inhalation or smoke due to visibility. You'd hate to have at 35,000 feet, not only could you not see, but now you're breathing in toxic fumes, not to mention seeing flames spread. So you start to see the performance of all the different regulatory items is based on the ease of escape versus the severity of the test. I'll get into how this is accomplished in the materials section. But if you're dealing with mass transit and they have a low tox, low smoke, that automatically takes many of your material choices off the table. So understanding this element will now zero you in on those few items from a regulatory standpoint. Green is another one. It doesn't have much teeth yet. Industry behemoths like Walmart are starting to build their own based on carbon footprint, not so much on what feels green and what doesn't. So where polypropylene, why is polypropylene better than, say, PVC or polystyrene, isn't so much on one's friendlier in the ground than the other, it's how much energy does it take to convert that particular polymer into the usable device versus end of life. So they look at how much energy is involved. And polypropylene and polyethylene, as Peter pointed out on a unit basis, it's cheaper to make. It's less cost intensive to get polyethylene than it is to, say, PET. The other one that we're going to start to see here, and it hasn't reared its head yet, but this dichotomy in the medical profession of hospital-acquired infections. These bugs are getting very, very dangerous, and they like high surface energy materials. And you look at some of the flame retardant grades are great for flame, but there's thousands and thousands of deaths due to MRSA and SARS and various other things. That's going to start coming out. That's going to be a mega trend. And so polymers that are eventually going to combat these are going to have a higher value than those that, from a flammability standpoint. It's more dangerous these days for these super bugs in an MRI than to think you're going to burn alive in one of them. So that's one of the, I'm waiting for that shoe to drop. It's going to happen. From a tooling standpoint, is it existing or new? This gets into the timing element of it. And I'm going to talk on a topic that I'm passionate about, both from the injection side, extrusion, and thermoforming side, is shrink rate. It's one of the most commonly asked questions. It's one of the most misunderstood topics. So I'll touch upon that in the next couple slides. Obviously, the configuration of the tooling is important. If you want a high-gloss TPO and you have to use a negative mold where the A surface is on the inside, you're going to lose a high gloss. It's not going to look glossy. So depending on how that part has to be made based on your geometric or part limitations will then alter your material choices. Plus, whether that was a positive or negative mold 2 will affect the shrink rate. From a tooling materials, especially with some of the more difficult, finicky grades like TPO, products like composites and wood tend to have a fairly easy time with the styrenics. Versus you get into some of the polyolefins, you try to use a wood tool, you'll have little pieces of wood on every part you make until there's no tool left. Now again, getting back to the Olds 88 and Phoebe on Friends, I have seen some innovative folks out there try some surface preparation to these wood tools to be able to get away from that. So there's, again, challenge what you think you know in trying to find solutions based to be able to utilize current options. Shrink rate. How do I get a part shrink? I just asked, I call the resin guy, right? He said, Craig, what's a shrink rate of 7,200? I'm going to cut my tool to that. And Craig's going to, I'm not going to give you that because chances are, well, you're right. Craig doesn't know, so I'm going to say, Rob. There's a whole pathway to get from A to B, and I just want you to be aware of it and how the right way to go about it is, because you still need an answer. Your tool guy's like, look, I can't cut a range, so don't give me a range. I need a number. So you're stuck with a hemming and hawing material guy and a tooling guy that needs an exact number, and how do you get there? Well, some of the areas, and they're color-coded, or could be material dependent. So the minute I put, let's say, a cap layer, a high-gloss cap layer, now I've changed the shrink of that overall sheet system. It's raised a bit if it's a high-gloss TPO. Color. Now, you telling me color affects shrink? Yes, it does. A highly loaded white not only will shrink less because the titanium dioxide acts like a filler, the part stiffness will feel more stiff. We're working with thin gauge TPOs for paint films. The white always felt more stiff than some of the lower filled colors in terms from a color standpoint. So we found that the shrink rates were actually different. They actually had to find that middle ground of taking white on the far end and one of the lesser loaded colors like a cave brown on the other and find that midpoint. Now we get into our realm, the sheet part of it. Now the shrink number is supposed to be unitless. It's supposed to be per something, and usually in percentage. But I've witnessed firsthand, as Ed can attest, we had some thin gauge stuff that actually had a chrome film. The stuff didn't shrink at all from our measurements. It shrank so very little. When we originally built in about 7 thousandths inch per inch, it was like 1. And so the TPO was so thin that the film's shrink rate, which is almost nil, took over. So understanding thickness as it plays a part, conversely, a very, very thick sheet, if there's internal stresses, you almost get the effect that rotomolders deal with, and that's how those different layers cool, so you have those inherent stresses. You can actually see warpage, what looks like higher shrink, was really a stress relief in one direction or another. Orientation, if while we're extruding, we intentionally pull while it's still impressionable, or we intentionally not pull and only do as little as possible, we can actually put inherent stresses into that sheet. This is intentionally done in polyethylene, as we know, so that polyethylene just doesn't turn to water while we're melting it in the thermoformer, so we get that stress as it keeps the bag up. Orientation, I used to believe, again, going back to challenging what you thought you knew, the idea was don't put any orientation in TPO. We've actually now had some programs where you need high orientation, as long as it's consistent. The worst thing you can do is have inconsistent, do 12% on one side and 30 on the other, and you're going to have problems all day long. So just understanding that dynamic is important. Of course, regrind I've already touched upon, whether it's self-generated, whether it's bought on the outside. Remember, it's easy to say, but there's garbage in, garbage out. And we test regrind that we bring in. I don't know if you saw a guy named Rod William. That's really all he does all day is test regrind, just to make sure, because the pain of getting it wrong is high. And so we make sure that we're looking at it very astutely. You get into the forming end of it, of course the process makes a difference. How hot, how fast your RF factor or your radiance factor of your heating elements, how old they are, that all plays an effect. Tool temperature, not so much on a unit-to-unit basis, but as you make more and more parts, you build up more and more heat. So the heat transfer coefficient, how much heat you're pulling out, can also affect shrink rate. And sometimes this is good. If you find out your parts are oversized, you just run them hotter or the tool hotter, or you end up doing it in greater succession. You can actually get some additional shrink out of them. How hot do you take them off the mold, especially the semi-crystalline materials that need that time on an impressionable surface to maintain their shape as they crystallize. If you pull off, let's say, polypropylene and throw it on the floor versus letting it sit on something that helps remove heat or at least control the dimensions, you can get vastly different dimensional results. That hand-in-hand post-mold fixturing. So if you can't use the tool, are you using something similar that helps give you that dimensional base so the part doesn't see additional shrink? This is why negative molds or female molds tend to shrink more, because there's no tool to stop them. So versus going over a positive mold, that tool will not allow that part to shrink anymore. So you find that dynamic, even with the same material. Trimming, especially those impressionable semi-crystal materials, TPO, polyethylene, if they're trimmed shortly after forming, you can sometimes get additional shrinkage and warpage than what you do if you just left the hat on for an hour or a shift or a day. And then lastly, if there's any secondary operations that involve additional heat. And what this is basically taking whatever stresses that were induced during, some during extrusion, but mostly during thermoforming, are relaxed. I like to use the bumper analogy as one. If Craig's talking to a customer in injection molding about a molding color part, and they decide to paint it and bake it at 250F for 30 minutes, the part's going to be smaller. So you'll often find if there's a molding color part and a painted part, usually you have to use two tools in the injection molding world. So just be cognizant of that. If you think everything's hunky-dory when it leaves your place and it hasn't been painted, it's been primed, and your customer puts it in his oven, it's like, this thing doesn't fit. So this little shape here was intentional. Don't get stung on shrink rate. And one way to do that, he's like, great, you told me all these things that affect you. Still didn't answer the question. What do I cut the damn tool to? So this is what we've advised, and I've done this on the injection side as well, is try to get the same material option or options that you want to look at and get them in and of the size that you can. Regrind level, cap layer. Try to get as close to as you would order it in production as possible. Extrusion direction is important because even if I try to control and keep orientation low, just the nature of extruding something in one direction creates an anisotropic behavior. So you'll find a square sheet, probably not that big a deal. But if I extrude something that's 110 inches long by 24 inches wide, and then I ran it the other way, you'll find dimensionally they'll be different. So try to make sure as you bring it in, it's going to be of the same configuration. And simply form it on your equipment with a tool that's similar. Even when it's not that similar, it's still better than me going to Craig or Karen or Gary and, can you give me that injection molding data sheet data on this little tensile bar or little dog bone this big? I'm going to cut a really expensive tool on it. And your data sheet's got a big disclaimer that says I'm not responsible, but I'm okay with that because if it's wrong, you can see where this goes quickly. And that's why you get a little hemming and hawing, because they don't want to see you make a bad mistake. And do more than one part if you can. Obviously, the more data set as possible, the better off. And if you're still on the fence, the best thing to do is take a page out of what they do in injection molding. And it's better to go what they say steel safe or ceramic or aluminum safe, is build it a little bigger. Because through all those things I just showed you, it's a lot easier to take more shrink and allow the part to shrink more than the other way around. But use that as a means of last resort. Again, fairly straightforward is equipment capabilities. And some of these materials, and when I get to the material pyramid, where we'll be sampling where the next material is coming from, you got to make sure you've got equipment that's capable of running it. Peter outlined the growth of TPOs. That was doing one part of the grades getting easier to work with. The other was the extruders being able to extrude them better. And lastly, the thermoformers had to make some significant changes. So if you had cal rods or you had gas catalytic, chances of your success in making TPO consistently were much lower. So that's why you see more ceramic and more quartz, more control. But making sure that as you look at the configuration of forming parts, do I have enough sag control? Do I have the ability for this part to hang on the top, which you might be able to use gravity? This is a whole day in and of itself that we can look at in terms of design and equipment capability, but this does play a role in picking materials. The supply base. Again, I talked about biases. We're probably not the best source if you want to talk about polyethylene. We don't run it. We're not that good at it. But we run about 65% of what we do is TPO. So that we probably have some good options for you, at least be able to talk through the different pros and cons. That's true for our competitors and colleagues in the industry is taking a look at their expertise, is what they have. You know, sometimes what you need, somebody may not have, and making sure that you're not shoehorning in what's offered versus what's really optimal can sometimes be that decision tree that you have to face. Obviously, the support that you get is key. We have a potential client in Australia. These guys need a lot of help, and so they're likely to look to us to help them across the board in these topics, and probably end up, you know, not going with price as the #1 property, which we'll see in one of the other topics. You know, and then the obvious ones: financial health, lead time, responsiveness, and do you have the managerial support? You know, some grades, and I've worked for companies that offered a product that didn't really want to offer it. You got to make sure that you got the top to bottom support, that that's a strategic product that they're going to continue to offer and not eventually rationalize down the road. Price is a property. We deal with it in our daily lives, but it's just that. You find that there's a key difference between how much something costs per pound versus my total system cost. We run into this all the time when we look at people favor some of the lower cost standard TPO grades versus some of the higher melt strength grades. Well, the higher melt strength grades cost more, but we had more than one customer go back to them after the cheaper stuff because they found a higher yield. They made more acceptable parts. So it's that balance of understanding the value point of that particular grade. I'll talk when we get to the properties about the differences in density and how it affects, and making sure you're using that in your calculations. Peter touched on this briefly, was the polyethylene dynamic. With the shale gas that's found in the heartland, the Pennsylvania valleys, we have an abundance of the polyethylene feedstocks to the point where eventually some work has already begun where we're starting to look at how do we make a polyethylene-based TPO. Now there's right now current trade-offs in doing that. It's not as simple as we'll just switch over, but we recognize that that's coming and working with the supply base to start to say, okay, how do we start working on it now so when the need happens 5 years from now, when polypropylene continues to do this and benzene continues to do this, that we can offer that as a fallback position. But where a particular regionality comes into play, just be cognizant of it. I figured Craig would want to use this one in one of your slides, but I love complementary goods, and what you see here is a picture of a convenience store selling a bottle of Pepsi with a complimentary good. I didn't doctor that photo. That's a real product. But these can be just as important in selecting your material as what are you going to marry with it. Bonding is a huge one, especially when you talk about things that are easy to bond, like the styrenics, versus difficult to bond, like low surface energy materials like nylon and polypropylene. You get into the decorative aspects, film, paint, chrome. What's this thing going to have to look like down the road? Which then will also factor how you do your attachment scheme. Are they positive attachments, rivets, screws, Christmas trees, or do you have to use tapes or liquid adhesives? You get into some of the RFID, with labeling, stickers. Are they easy to put on? Are they easy to take off? We start to get into the recycling element of it. Are you a snowmobile manufacturer and you need the cold temperature ductility of certain grades, but I got a hot engine, and these fuels these days, these performance diesels are burning hotter and hotter and hotter. So do I have enough clearance? So I have to use shielding. How do I apply it? Water management through gaskets and glazings. Can I do that in mold? Can I do that bonding? Are these types of materials conducive to each other? And do I have to look at modifying an existing grade with certain fillers? Material properties. So really, it's the critical differences between tangent or secant methodologies in tensile strength. No, I'm just kidding. It's trying to keep this thing as pragmatic as possible, giving you the tidbits of information without trying to put you too far asleep. So what I wanted to do is highlight, at least in industrial thick gauge thermoforming, a packaging guy, somebody in medical, some of the regulatory stuff would say, no, that's not important in what I deal with. And I get that. I just had to pick 7. And through the years of parts like you've seen and that we've shown, these are the 7 I think are the most critical. But there could be others depending on your case. Specific gravity is an important one. And what specific gravity is really just a ratio of the density of one material divided by the density of water. In that regard, it becomes unitless. So specific gravity does not have any units. It's a comparison. And like we show with this pumice, it floats in water because it has a density that it's less than water, so it's below 1. You can start to decipher when you look at various densities of unfilled materials. You can figure out, are they polypropylene based, are they polyethylene based, just by this particular number, because they don't change if you're dealing with a neat polymer. As you start to add filler, the number goes up. So this guy will float and this guy won't. This becomes important for 2 reasons. One is, this is not density, okay, but it's related to density. So when we talk about factor, that's just a fancy way the industry is, I don't know, try to create a shell game, but specific gravity, you can find the factor, or if you're given density, that is the factor if it's in pounds per cubic inch. So we were to look at, how do I calculate the sheet weight? Well, if you're given the density in pounds per cubic inch, you just multiply it times your dimensions already in inches. That's easy. That's how much the sheet will weigh. But if you only know the specific gravity, let's say you want to use this 0.9, you multiply it times the density of water in pounds per cubic inch to get the factor. All demystified. I know, I've just revealed all the dirty secrets. It's really not all that revealing, but that's really what we do when we try to calculate sheet weight. So we'll take the specific gravity and multiply times the density of water. Now what makes the SI units kind of nifty is density in metric is the same. So the units are 1. You only have to multiply it times 1, not this big hairy number down here. So if you need to know your sheet weight in kilograms per centimeter squared, you measure it in centimeters, it doesn't matter. The density is the specific gravity because the units are 1 for the density of water. We don't run into that too much. It's still fairly an English unit dominated industry. So how do I calculate that? And this is an old tired slide, but I use it for illustration's sake. Let's say we take a 250 thousandths thick sheet. I got 2 materials, material A and B, and B costs 10 cents more a pound, but they have uniquely different specific gravities. So let's calculate. Material A, want to know a square foot, 12 times 12 times the thickness, times the specific gravity, times the density of water, times price per pound. That's how much a square foot of material will cost. Now of course, you know what the next one, it costs more, but it's going to cost less in the end of the, you see with the animation here, is because the density differences are so much lower for this guy, even though the price per pound's higher, the sheet price is lower. And this is important, especially when we're looking at, I'm supplying a sheet or a certain amount of square or cubic area to know what your sheet cost is going to play a factor in. Flex modulus is important. As I mentioned, the resistance to bending. This is a 3-point bending test where this ram comes down to measure how much force it takes to displace X amount of area. And it is a function of thickness, as we went through, that geometry is important, as well as speed, the silly putty with tensile. What you'll find is to get a higher value, if you like a certain material, there are various fillers that are out there to make this higher. Usually it starts with your minerals, whether it's calcium carbonate or talc, which is more common for TPO. Then you look at glass and carbon fiber. Now you're starting to get into more exotics where your processors like extruders like, I don't know if I want to run glass, it's tough on my equipment, the aesthetics are compromised, et cetera, but it will give you a higher flex modulus. So a lot of your structural materials start to look at dramatic fiber reinforcement to get this, especially if that's the #1 important property. You'll sometimes find that it's measured in pounds per square inch, which is a little easier for us to get our head around. Sometimes you'll see it as megapascals or gigapascals. It's easy to convert between MPa as you multiply times 145, and you'll get it in PSI. There's also a cool function. If you go to Google, just the Google search, you type the word convert, and say convert 14 MPa to PSI and hit enter, it'll tell you what it converts to at the top of the search. I'll demonstrate at the end if those want to see it. There's also a number of conversion widgets, and there's an app for the iPhone that will convert various engineering properties, currencies, some pretty neat stuff if you've got to talk, especially helpful when we're dealing with temperatures or metric to in English. Tensile is, I mentioned, with the tensile strength of concrete, but we look at a test that comes to us from the steel and metals industry. It's carried over to plastic, and really it's the rack of doom where we're pulling a type of material and see how it behaves as it goes to the elastic deformation phase, to where it yields right here, to plastic deformation. This is where plastics gets its name, meaning I take it to this point, it's not going back. Versus if it's elastic like a rubber band, I do my stress over my cross-sectional area and it'll revert back. Once it gets to this point here, it's the point of no return. So this is important to know in failure mechanics where tensile is important. Impact resistance. There are a number of ways to look at impact resistance. And there's a reason why the NTSB and other agencies look at crashing full units, because this is a dynamic event. So when you look at how things break in systems, they deploy airbags. The only way to get data is to deploy an airbag. You run a car into a post at high speeds, because there's a lot of things going on that even computer simulations can't figure out. So to be able to get it to the real world where we're looking at it on a material basis, we've come up with some various tests to try to mimic how these dynamic events appear into the field, where you're hitting something with a 9-iron, or you're bumping into a post, or someone's throwing lawn darts at you. These tests are trying to mimic the best impact methodology so that we can look at data to make decisions. I point out 3 here. The first one I'm not crazy about. IZOD, whether it's notched or unnotched, or the real fancy version where you throw it on its side and you call it Sharpie. I have not found in the materials that we deal with that translate to field performance. It is a useful methodology, especially with ABS and some of the styrenics for IZOD to determine a higher impact grade to lower impact. But I found that the other 2 tests seem to give you just as good data without some of the noise. Gardner is a falling dart, uses gravity, so it's calibrated every day. It's just a weight with a head on it, a tup, and you measure how high up. So if you got an 8-pound weight, 10 inches, that's 80 inch-pounds. And you're looking for whether you get what's called a fail, like here, or a pass, like here. I will point out, though, that Gardner does stipulate that only half of the samples have to pass at that particular temperature. So if they reported at 200 inch-pounds, half or better passed it, not 100%. So just be aware of that. The other is a more fancy, sophisticated piece of equipment called multi-axial impact or instrumented, and it's almost like a falling dart except it uses constant velocity. Gravity is an acceleration. This uses a constant velocity and will puncture through the sample. So your parts don't look like this. They'll always have a hole or they'll always have that, and it measures the energy under the curve. The thing to keep in mind is, again, follow the rules from the first half. Don't fall in love with one particular property, but look at a couple. How does my impact performance with Gardner, with multi-axial, and any other corresponding data? Heat deflection temperature, or sometimes called deflection temperature under load, or DTUL, is similar to the flex test, except in measuring how much force it takes to get to a certain level. You keep the force constant, and you keep raising the thermometer up in an oil bath. So what this determines is at what temperature does this material soften to the point where it bends X amount. You often see this under two different loads, 66 psi and 264. This is one data point of determining the heat resistance of a particular grade. Again, remember, design's important. So this, whether it's at room temp or 230 degrees F, if your part's not designed to handle heat, it can work against you. Annealing can also, when you're looking at data sheets, make sure you figure out if it says annealed or not. You can bake these, if you remember cheese and crackers, you peel away a thing, you get a little thing of crackers, and they give you this red, I don't know, it's not a spoon, it's just a stick. Well, that's what an HDT bar looks like. So that data is taken off that little guy. And so if I bake that little piece of plastic and take some of the stresses out, I can improve this value by about 10 degrees. So it's important to understand whether you're dealing with annealing or not. When I said don't pick one particular property, I actually had a customer back in 100 years ago saying, I have to have X HDT. I have to have it. And the reality is he didn't. He fell in love with that particular property, removed a lot of options from the table, and ultimately ended up hurting his particular application's success rate. This one's a mouthful. CLTE, or coefficient of linear thermal expansion. This is the expansion contraction behavior of a part. This isn't shrink rate, although they can be related. This is a part in and of its form that when it sees a temperature extreme, it reacts. Now, most everything, when they see higher temperatures, especially solids, expand. Water is actually one of the only materials on the Earth that when it gets colder, it expands. Most everything, when it gets colder, they contract. So what you're trying to do with this particular part, especially as parts get bigger, is you need to understand this because this plays a key role in fit and finish and dimensional tolerancing. The temperature in this test specifications don't give us a lot of help. Even ISO standards don't mandate a range, or if they do, it's very limited. I mean, 30C is just above room temp. So you want to be able to make sure that particular polymer, you're going below the glass transition temperature and likely above it, so you know the worst ends of the spectrum. Well, that's great. Well, how do you calculate it? Now, I know this is wordy, but what it's saying is if you get a value for a particular material, and this is what they usually look like. So if you were asleep in math class that day, 10 to the minus 5 just means you're moving the decimal point forward 5 spots. So this particular material, that's its thermal expansion value. So if it's a 48-inch long part, you say, all right, here's my temperature extreme. 23 to room is 95. 73 to 176, 103. So this is going to be our cold. 95 times 48 inches times this number here. You're going to contract over 100 thousandths. You look on the hot side, room temp to that higher end is 103. You're over a quarter inch. You add these two together, so you go to the coldest of Minnesota and the hottest of Arizona, you got to accommodate for almost a quarter inch. And this is a pretty low thermal expansion number. Polyethylene's 4 times this. So this becomes a critical part when you're doing your design and tolerance. Surfaces. Hardness can play a role, especially in the TPEs. If you're doing floor mats, you're trying to navigate the whole world of elastomers, the number one property that you'll start with, because that'll then help framework the next choices, is hardness. The harder materials tend to go on the Shore D and the Rockwell R scale, the softer materials on the Shore A scale. The lower the A, the softer it is. The higher the D and higher the R, the harder it is. Unfortunately, there's no conversion. These hardness scales, they overlap, but there's no calculation. So you just have to find where they overlap and understand that a 90 Shore A is about a 40 Shore D. I don't know who came up with it, but it's an imperfect way to look at things. So if hardness plays a role, and that's critical in sealing, your glazing, your weather sealing, they live and die with this and compression set. Then you get into some of the gloss and surface dynamics, like distinctness of image. Really, this is just a couple different ways of how does this part reflect light, and how much of that light is intact when it's reflected. I use the example here up close of these are two products that would measure high in a gloss meter. Someone's asked me before, what's the difference? Why is DOI and gloss different? They're the same, right? Well, these will both measure fairly high in a gloss meter. This one will measure higher on distinctness of image because if you look, you would actually see your face or this light more crisp. There's fancy pieces of equipment, there's basic pieces of equipment to achieve this, versus this guy here, which has a high degree of orange peel or scatters light, would have a lower distinctness of image. Ford Motor Company, before there was actual devices to measure this, would actually have paint standards that had heavy clear coat to say, yeah, that's a 4, that's a 3, or that's a 2. Just understand this dynamic. This becomes real world. If you get a part and you're made it up to fiberglass, you may find that the gloss numbers look the same numerically, but the parts look visually different. And so it's an understanding that from a harmony standpoint can be a factor. The scratch and mar, I mean, that's a whole topic, so I'm just touching on these, that they're different. Know that scratch is a physical trench through a material. Polycarbonate's difficult to scratch. It's easy to mar. Mar is a micro scratch, so where you've taken an optically clear surface, it's easy to take, say, some rough, coarse paper towel and not be able to see through it like your eyeglasses, which are typically coated. It's the mar resistance that left me with tail between my legs after I left Moline, Iowa. And that's why we look to add the acrylic, because it has excellent scratch and mar. Just understand that there's differences in the two. I mentioned a word about data sheets. They are a resume for a particular product. You know, I leave off my resume that I'm a Star Wars fan club president because I don't think it's pertinent. What you find, joking aside, is that you tend to leave off what incriminates, and you tend to expound upon what becomes valuable of that particular material, and you accentuate it. Again, beating the TPO drum is you don't see a lot of structural data on TPO because it's not a good high creep material. It's got other benefits, but structural design isn't one of them. And usually the data is provided by the company who produces it. Very rarely is it validated by a third party. I mentioned earlier, a lot of this is done by injection molding specimens. Understand that extrusion is a different process and you can yield different data. Usually when you get a data sheet, a product could have been around for a week, could have been around for a year, it could be an industry stalwart that was developed back in the 60s. Knowing what development period is important because you'll find as raw materials change, as that grade develops, it can take on some various different properties. And like I said, these guys it's just like going to Home Depot and getting lumber. If you build a house and it falls down, it's not Home Depot or the lumber guy's fault, unless it's bad lumber. And so you'll see that type of not suitable for use language in data sheets because they're not saying that this stuff will work in snowmobile hoods. They're expecting you to make an informed decision with the data at hand. All that, and I'm just now getting the materials. Well, there's only a handful. As Peter indicated, the menu that's offered to the extrusion thermoforming industry, unfortunately, is limited. We're starting, and others in our industry are starting to challenge that. But it is a finite group, and we'll touch on a few that we may be seeing in the future. If you look at the pyramid of plastics, this basically plots with a few exceptions, about all the available materials that are out there for any process. How it works here is it's divided by amorphous and semicrystalline, and I won't go through the technical differences. Just know that they are a little bit different in behavior. And the shape of the pyramid is important because the base of the pyramid represents how much use or volume thermoplastics are out there. You know, those guys who live down here don't like to be called commodity. But really, that's when you look at the usage in the world and the recycling symbols, you know, there's a reason why number one's PET, because we use more PET in our day-to-day lives than, say, PEEK. And they tend to have a volume versus price performance balance. Now, where they fall in this can be argued, but you're not going to find these guys down here or these guys up here. This is important to look at, too, because if you were to pick the top thermoforming grades that have been available the last 25 years, you're going to find the majority of them reside down here. A couple are up in this area. These tend to be the no man's land, which has been almost a good old boys club of injection molding. And as we start to look at how to grow our pie, what's new? Nothing's new. Well, there's a bunch of stuff up here that's untapped. Keep in mind, TPO really didn't gain a foothold in thermoforming until about 2003. And even then, it was a lot of bloody noses and black eyes. And that product came in injection molding in 1983. So you're talking 20 years, which is not surprising. You look at the cell phone, from when it was invented to when it became in every one of our pocket. You can't keep it out of 10 feet of your reach. You looked at macro megatrends. I went to a conference about 8 years ago. What's the next megatrend? Oh, artificial intelligence. You know what came out? Text messaging. We've been able to text message since the days of Speak and Spell. So it was something that existed that took 20 to 30 years to come into existence, whether it's the internet or its materials, that's right there on that board, and combinations of these are what's going to be new. TPO and acrylic aren't new. We're just now able to bring them together into one system. So as we look to, yes, Peter?
You could add fluoropolymers in there too.
Yes, the PTFEs.
Silicone, which is a big innovation in injection molding.
Yes, and the fluoropolymers what's funny is we use them as process aids. They have an affinity for metal. They help keep dye lines and dyelet buildup. But to use as a single product, all your pampered chef stuff, majority of it's silicone rubber. Stuff's excellent material. It's expensive, and trying to find out how to incorporate it with other resins, you're now saying, all right, for me to look at this as a processor, before I can even offer it to you, I have to have specialized equipment. If I want to offer this stuff at the high end of the temperature range, I have to now have new barrels, new screws, oil temperature control versus water. So we're starting to look at that as saying, where do we position ourselves so that we can at least offer it, and then you can start thermoforming it and then offering it to the end customer. But this is the future, is we're just going to start to swim upstream of this pyramid. Or we're going to say, let's take this guy and bring them together. Those that are offered to us, and this is more basic remedial and probably at best a review, polyethylene obviously is on a cost basis per cubic inch is one of the lowest cost materials out there because it's the simplest molecule. It's carbon to carbon with a couple hydrogen hanging off of it. It's highly organized candle wax when you look at it chemically. What you get out of that is excellent impact. You get very good chemical resistivity, but its limitations come in flex modulus. You tend to have a peak, probably around 190, 200,000 psi flex modulus. It has a very high shrink and thermal expansion. That's why it's so affectionately called polywarpylene. And it's tough to bond, tough to print. But if polyethylene works, use it, because it's a low-cost material. It does a number of great things. What I have witnessed, though, when getting in this in the beginning, I seen more high density. Now I see more high molecular weight polyethylene. I don't see too much high density anymore in thermoforming. They seem to have gone up that chain of asking for more properties out of the material. Also, it's one of the only materials, Peter indicated rotomolding. Their menu of products is even more limited because you've got to pulverize this stuff and move it around in a rotational mold so it turns to liquid so you can get the layer upon layer. Some of these other grades, to get them into powder, are too cost prohibitive to be utilized where you can pulverize them into powder. They got to be cryogenically frozen. And so, you know, rotomolding is polyethylene and what, maybe nylon and what else?
Polyethylene is about 93%, and you have nylon and polycarbonate. PVC was the original one. The problem with rotomolding is that it's such a long cycle that a lot of resins just get burned up by the time you're getting through the heating process.
So it's
It's a long process.
so the material selection presentation, and they just show this slide and say, have a good day? Pretty close? All right. Polypropylene, it's funny, it's Peter touched upon it, and some people are like, we're not going to touch it. The thin gauge guys have already, they're in it knee deep. They're getting a lot of pressure from guys like Starbucks to say, look, we love PET, but we want that green factor of polypropylene. It's got to be clear. You're looking at clarified polypropylenes for fruit cups and various, any airplane ride you take, almost all of them are polypropylene cups now. You can typically tell if you crush it and it stress whitens but doesn't crack, chances are it's polypropylene. I'd say turn it over, but I don't want you to waste the 3 drops of Diet Pepsi they give you to look if it's recycling symbol number 5 versus 1 or whatever. And there's reason why polypropylene it tends to have that higher flex, so it addresses the issues of polyethylene. It has a higher HDT, but it doesn't have the impact resistance like polyethylene does. You do see the hybrid between the two of copolymer polypropylene, and that's what like Tupperware uses, so you're trying to gain the benefit of both. Make sure the lid doesn't warp on you in the dishwasher, but also getting some of the impact resistance, so if you drop that spaghetti sauce out of the freezer. But just like polyethylene, it has its limitations for bonding and painting as well. One interesting thing about polypropylene is if you're looking at a living hinge design, whether it's one-time or multi-use, whether it's a flip cap on a shampoo bottle or whatever, polypropylene-based materials have excellent living hinge properties. They can go through thousands of cycles of over, open, close, open, where other materials will have fatigue. I've actually watched some pretty innovative guys form a twin sheet living hinge just to bend the part so that they could have a unique geometry just one time. They just wanted the hinge to work one time, and then they reassembled it so they could ship these things flat. So you're not shipping air. So just a kind of toolbox tidbit. Polystyrene and its bigger older brother, high impact polystyrene, which is kind of like saying jumbo shrimp, but compared to polystyrene, it is high impact. It's pretty inexpensive. It's massively easy to thermoform. It's what we worked on in school because it's so easy to thermoform. You're not going to drop something in the oven. And because one of the cons, it has low chemical resistivity, it's easy to bond and print to. A lot of your old models that you may have put together as a kid are polystyrene, and so the adhesives are cheap and easy, and they bond together. You get a good chemical bond. Even from high-impact polystyrene, is they're really on the lower end still compared to the other materials we talked about in terms of impact, and by themselves are not weatherable. What is also interesting I found is any of these materials, styrene-based, including ABS, we've all heard of fiberglass, which is a styrene monomer with a woven glass chop. That monomer styrene will not bond to polystyrene or HIPS or ABS, even though styrene to styrene. We find customers in the marine industry who want to make an ABS console for a pontoon boat, want to reinforce it with hand layup, actually have to have a layer of acrylic on the backside to be able to bond that chop to the other part, which I found it's not intuitive because you think like dissolves like, and you should be able to bond the two. And the truth of the matter is they won't. ABS, a terpolymer of 3 different ingredients, as you see listed up there, continues on to the styrenic theme of easy to thermoform. You get also a better impact position, and this is why a lot of the home appliances growing up, whether it's from the that big heavy red telephone that hung on the wall to any of your electronics. ABS had a good dimensional stability, good household impact, and easy to process in any way, shape, or form. But similar to HIPS and polystyrene, it too has challenges with chemical resistivity, as well as weatherability. So usually if it's dealing with some sort of exterior weatherability, it goes along with a cap. And like we've seen in some of the TPO successes in the 2000s, is because it was easy to form, it was often positioned in applications it possibly shouldn't have been in. That's where we get into stress cracking of a large part exterior where there's vibration involved, and that's where TPOs had a big success factor in. The decorative options, keep in mind the consideration, they can be films, which are either inline or offline laminated like we do with our decorative products, or we can co-extrude, like Arkema's DR101, which is an industry standard, or the Solar Coat line of grades. And there's some differentiation between those as well that we can go into if you have any questions. Or ask Arkema, because they're here too. I beat this drum all presentation, so we know what the pros are. I touched upon some of the cons. A lot of it, from a process standpoint, there are now options. We indicated that the supply chain's gotten better, more cognizant of its limitations, and with some new innovations, we've hoped we've addressed a significant one here in Scratch and Mar, either with a decorative film or a three-layer product. I do want to point out, maybe about 10 years ago there was a one-size-fits-all. Now there's a number of different performance cap layers, like high-gloss polyolefin. So this gives you, instead of a dull product like you saw with the green extruding today with the hair cell, we can put a high-gloss finish on it to bring up some of the luster. Also, we offer various interior base grades where you're dealing with a dark pastel where you're trying to make sure that high occupant contact, like an instrument panel, somebody doesn't take their keys across this particular color. We're really formulated so you don't see that scratch whitening, which is different than another cap product we offer of stress whitening, where you see here where this has had a blunt force and read through, where you get basically an evacuation of pigment. It's past the tensile yield point on a microscopic level, and you get whitening. So there's cap layers out there if you're having to do like a charcoal gray, and things going to get beat up from the behind like a wheel well cover. You're getting a lot of rocks. You might want to look at getting a particular cap layer. Interesting enough, black hides this. Dark gray, worst color for it. So it is a color-dependent type of phenomenon. And I know some of you in the audience have wrestled with this exact topic, and we've tried to do our best to help you work through it. There's also a whole myriad of soft touch grades out there, rubber type, as well as we touched upon some of the wood grains and carbon fibers, but I do want to iterate that there's a chrome options out there as well as brushed metals and a handful of looks to help give the decorative jump. This, you think TPOs are convoluted? This whole TPE family, Peter touched upon silicone or fluoropolymers, there's fluoroelastomers. You get into silicone-based elastomers. You get into polypropylene-based, PVC-based, styrenic black copolymer-based. You need a map and a tour guide and a GPS to navigate the worlds of TPEs. So I just give you the highlights and just know that there's high heat versions and under hood. But by and large, you're looking at these to try to get the rubber-like behavior, low gloss, soft feel, elastomeric recovery. So if I make this format and I roll it up in the box to ship it, I want to pull it out and unroll itself. I don't want to have a plastic memory. You find, by and large, in thermoforming, these grades tend to increase in gloss when heavily processed. So the WeatherTech mat that are popular in the Cabela's catalogs, those are formed at a very, very quick and low temperature, because if not, you'll see a gloss increase, which is not desired by the end user. You can find stuff that's pretty low cost. You can find stuff that's pretty high cost. You really have to know what you need so you get what you want with these types of products. And what you also find is the lower hardness you get, the poor mar resistant. You can, on a real soft, like a 25 short A product, very flexible, sometimes used for syringe membranes, is you can take your fingernail like velvet and write your name in it because they're so soft. It doesn't really, you can't take material away, it's just they're not real suitable for a lot of high touch applications. So most are melt compatible if they're polypropylene or SEBS based. Some are not. So I just, the conclusion on this side is if you don't know, we can certainly help you navigate these waters. We do run our share of polycarbonate ABS, or PC ABS as we call it. This takes that next tier to get a higher flex modulus. This is also what I would consider a structural plastic. So you got something that's big and bulky like that hood enclosure. PC ABS is usually a good place to start, especially if design is not on our side. It has very good impact resistance. And what you find is it doesn't need a primer like say TPOs or some of the low surface energy materials, but it does need a cap layer to remain weatherable. So again, whether we're using a film, a coating, or an actual co-extrusion. It's not cheap, and it can be challenging to process, especially when we're talking twin sheet. TPO is pretty sticky, so it's fairly easy to twin sheet. PCABS, once you get outside that window of bringing those two materials together, it can be a challenge. Now we do find that this is about, on the current slate of products, about as high a flex modulus you're going to get before you start to look at fiber reinforcement of any grade. So if you don't want to have to use filled, glass filled or carbon fiber filled, these types of grades are going to be at that pinnacle of what's offered right now. Flame retardant is also its own category, full day topic type of thing, and we do run some flame retardant products, ABSs and PC ABSs. There's really two ways to go to get flame retardancy, and this is in the easy to escape stuff, not the aircraft like I showed earlier. And one is you go inherently flame retardant. So what I'm referring to is acrylic modified PVC. What happens when these things are lit on fire is they naturally oxygen scavenge based on the chemistry of the material. You don't need an additional flame retardant additive to make them FR. So what that nice is you don't have to put a bunch of junk in there you don't want that hurts properties. So this is the reason why Kydex and Voltron and a handful of others, this is a natural first entry type product, the Royalite grades for FR, because by themselves they're flame retardant. The other route is to take something that isn't polypropylene based, ABS based, and say, look, I need to add some fillers to it. This gets tricky because some of the best flame retardant fillers are brominated or halogenated compounds, which Europe and others are starting to say, no, we got to deal with end of life stuff here. We're not putting the stuff in landfills. We actually are incinerating it. So we burn this stuff up. Intentionally, it's bad. So knowing the options and latitude you have here will really either open up or narrow the scope when you start to look at your menu of options. Obviously, the pros is they don't burn. And these fillers or particular grades tend to also enhance the stiffness of a product. So an FR TPO is stiffer than a regular TPO. Same with ABS and PC ABS. It's really the only place you're going to be able to look at if you've got some of these regulatory items like this MRI enclosure. You know, if they put I have to have a V0 UL burn, then you're looking at an FR grade. No way, shape, or two ways about it. Similar limitations on the base grade, and again, these things can get costly. I do want to point out, because some of these fillers on the second option tend to be white in color, to get a vibrant red or a jet black is near impossible. You can get pastels, but these fillers can combat the colorant. If you add too much colorant, I'm taking less FR and putting in more color concentrate, which isn't FR, and I can hurt my rating. So when you're talking about with a customer and he's like, yeah, I want to do a candy apple red and a jet black, go, wait a second. that may determine which path I take in terms of what you're looking for. In closing, I put together 4 case study scenarios of how in quickly. So it wasn't a lot of in-depth type. I just give you some thought process of 4 unique scenarios that have a little bit of touch to reality, but not so much I'm going to get myself in trouble. And I'll close with these and see if that sparks any interest in question. But thought I'd walk through part 1 plus part 2 equals this in a snippet vignette format. Case study number 1. Let's say your customers come to you and say, I want to do these energy management cones. These are thermoformed parts that you'll never see, hopefully, that sit and reside, say, in an instrument panel or an A-pillar. And their design is to manage energy. So let's say you get in an accident and your head hits the A-pillar. These cones are designed to crush in such a manner that it catches your head, not provides resistance to where you turn into spatter on the A-pillar, or it hasn't crushed enough and you don't have any energy management and you hit the steel. The guy comes to you and says, it's an existing program, I got tooling, and I know I need polypropylene, it's what's work, it's what's spec'd in, but you can't get it here. It's only available in Europe, and this is the grade we're using. So one approach, a tool that I've used often is MatWeb. Another good one is IDES, which I think UL is now combined with. Some of these are for pay, but you can navigate around with them and get some some at least free information out. In knowing that they want, a lot of the thinking's already been done. You just got to find something that's available here. As you go through this, and you'll find there's a number of queries. First one, of course, going to polypropylene, and then I said the next line here is we want a melt flow rate. So this tells me it's not injection molding. And start entering these properties as listed here. But what you'll see is I gave a range. Again, I wasn't quite sure what test methods they used to get there. Plus, it's an injection molding specimen. So if I give a range, fairly comfortable on either side of the spec, that's going to give me more options. And I went through this, and I got a list of about 10 or 12 grades. And you can use this free service, and it'll say which ones are commercially active in North America. And it'll give you a list of vendors, or you can do a simple search and say, hey, these guys they produce the product in Europe, but do they have a distribution or such in North America? Or if you find an approved source list, you can sometimes find an equivalent grade as well. That one's kind of easy. What if I had an injection molded running board and these guys realized that it dropped in volume? So injection molding doesn't make sense anymore. It's a TPO that they paint. They want to look at thermoforming. But you take a look at the backside of this guy, and there's some return flanges and some attachment methodologies to hold a 300-pound bubba that stands on this thing. You're given a Chrysler specification, and you got a rough idea what that means from the spec. Google's a wonderful thing. What you'll find with some of the automotive guys, the domestic OEMs, will publish the specifications, or you can typically buy them. Conversely, the transplant, whether they're Korean or Japanese, will sometimes covet these specs as intellectual property. Good luck finding a full, up-to-date Nissan specification on their current bumpers. That's theirs, and them and their supply chain make sure that that's controlled a lot tighter than, say, the U.S. OEMs. So be cognizant of that. You find in this particular instance, this old Chrysler spec, hey, there's a grade that's approved, but that one's obsolete too. So you're starting to then find the breadcrumb trail that you find that this particular vendor, who this grade's not available, they recommend some of these others. Well, you look at the properties here, are also similar to some other grades that are out there. So you find that now you've got options, and you can provide those to the customer, saying, look, I buy this one, I don't buy that one. Here are your 2 options, price point, that type of thing. Availability, that can play a role. Also, making sure that whatever you do use, do I look at a structural inner, do I look at twin sheets, and that it starts to segue into the other areas once you've been able to determine material composition. Number 3, let's say you got a heavy truck customer, it's a brand new program, they want to add a chrome accent piece, and they don't really know how to attach. So you got a dash that's traditionally a blend of vinyl and some decorative parts, and they want to put an accent piece either running along the instrument or the glove box or around the surround. You say, all right, chrome. I know 2 ways to get there. One is a dip process, and the other is to look at some films, decorative films out there. That still doesn't answer what resin to use. If I got to go dip for whatever reason, chances are it's got to be an ABS or a PC-ABS blend. That's going to limit my options. Plus, chrome dipping, and there's not a lot of outlets to get that. So one is to look at possibly a decorative film, since it's interior, and I might be mating up to other styrenic parts, and I don't need the exterior weathability. The chances are we may look at it capping an ABS. Doesn't need a middle layer to bond it to the chrome film, and can get you a nice dimensional fit and function as long as the temperature ranges are within control. Also, because in this case, looking at ABS, it opens up the number of tapes and adhesives that you can use versus what's available for TPO. I'm building in a number of these in and out that they all will affect depending on if you're told how it attaches may affect which option you go in terms of the base material. And then lastly, let's say it's what all thermoformers want to do. Sorry, Rex, outside of FRP. You're growing the pie. These guys said, look, I'm done with hand layup. I'm looking to get away from painting it and saving in weight. But it's a big engine cover, and I've got a 180 degree F peak temperature. Now, I notice I didn't say service temperature. This thing's only going to see 180 F, say 30 minutes at a time. So in a big exterior part like that, based on history, I'd probably shy away from ABS. Even though it's easy to paint, I got a lot of decorative options, it probably isn't going to take the vibration and stress cracking. I'd probably start with a TPO, but only if the design is good. If I find that I don't have a lot of geometry, this thing's a lot of flat area, or these are unsupported, they may warp, they may wave. So I start to look at, okay, if it's got decent geometry, probably go with a high gloss TPO or maybe the Stratagem option. If I don't have a good geometry, I may look at incorporating a high gloss TPO but with a heat shield blanket, like the snowmobile hood option. If it isn't favorable, I can't do any of those things, and I'm probably looking better at a PC ABS. I can take that additional heat and structural requirement. But I am going to be mindful working with these folks that a painted part and a plastic part tend to not have, to the eye, even though you've tried your best and all your gloss numbers are great, good part harmony. So I might want to make sure if they are going to touch, we've got some sort of separation or an accent piece. Just 4 ideas I had off the cusp of similar applications, not quite exactly the same that we've run across recently. That might help spark, how do I apply what you just went over the past hour or so and apply it to a real-world scenario? So wrapping up, I want to impress upon you these 6 points that the world has changed. The good news is you're not alone. Just like when there's any unmet need, innovation and others tend to fill the void and try to offer that. And hopefully you've gotten a sense from the tour and from what we've shown you today that PMC is looking to step that up and offer that additional service and support, take this journey with you and your firm, and I think as well as our supply base who's in the audience as well, and a testament to the support that we look to provide. Consider those 10 ideas before talking to materials, because those questions are going to come up. So if you have an opportunity to get the information up front as possible, you're going to have options that are more successful, faster. Be informed when you're talking properties. Understand that there's little nuances out there to be cognizant of, and that I really firmly believe that winning solutions, profitable solutions, are systems-based. Again, getting to not only one material, but multiple system where you're talking bonding, painting, complementary goods, and that collaboration is key. We like them to be brought to the table sooner than later so that we can be a partner in your success.